Okay. Hey, here's a pretty good challenging one here. This one says, we've got this drawbridge. It says, suppose that a 900 kilogram car is on the bridge, and they look at this figure, and I printed up the figure with its center of mass halfway between the hinge and the cable attachment. Okay, so if you go back to problem number 12, they kind of describe the drawbridge. I didn't print that one out, but it does say that the drawbridge has a center of mass and 1.5 meters away from the hinge and is 2,500 kilograms. So I went ahead and put that in the diagram because it's not really listed in this problem. You got to go back to number 12 for that. And then I could add a car right here and say, okay, gravity is pulling it down right at the midway point, and I'll put 900 kilograms. Now, maybe I should also put times 9.8 in my diagram to deal with forces. So we've got two weights pulling down. We've got the weight of the bridge itself and the weight of the car. And that's important here because we need to be at equilibrium, and the two conditions here are that the sum of the forces have to be 0. So x and y all have to come out to be 0. And the sum of the torques have to come out to be 0. And this is the one that you've heard me say a few times, and let me do it again, that there's kind of an advantage of doing torques, even though there could be harder, and that is for any force, and so in this case, the force at the hinge would be 0 because the torque can be calculated two ways, RF sine of the angle between them, or R perpendicular. Now, either way you want to look at this, for the force that goes through the hinge, the torque would be 0. And that's a nice thing to have in your equation if you don't know anything about this force and it's just kind of getting in your way. And, of course, in our question here, it says, find the force in the cables. So we'd like to find this force in this cable. We know the other forces and where they're located. We don't know that one. And so it seems like this is a perfect recipe to do a torque calculation first. So I will. And say, all right, let's do a sum of a bunch of torques and set it equal to 0. And I'll just go right through the line doing the torque from the weight of the bridge first. And I will use this equation, R perpendicular, because they give it to me as 1.5 meters. So it would be 1.5 meters, and it would be a force of 2,500 kilograms times 9.8. And then don't forget about the sign, whether it's positive or negative, and I want to emphasize the positive or negative has to do with rotation, not a direction. So I don't just look at this and say it's down and, oh, that's negative. Well, what I need to do is maybe put my pen or finger right there and pretend I'm pulling right here. And that would rotate this piece of paper. Let me pull again. And it's a pull. It rotates it in a clockwise direction, which is usually labeled as a negative. So that's why it would be a negative torque. It has nothing to do with the direction of the force. It has to do with the direction of the rotation. Now, same thing can be said here about where the car is. And so I guess we have to do the distance out. And let me just confirm here. I think it said it was right in the middle, right? The center of mass halfway between the hinge and the cable. And so it looks like the whole bridge is 9 meters because we've got a 7.5 here and a 1.5 there. So halfway of 9 is 4.5. So I'm going to use this formula to calculate the torque here and say it is 4.5 meters and its force is 900 kilograms times 9.8. And again, whether it's plus or minus, you might just kind of want to imagine holding it here and then pulling in the direction of the force. And you can kind of see that if I were pushing down, this would rotate my whole paper and the whole drawbridge in a clockwise direction, which is our negative direction. So both of these forces make a negative torque because they rotated in a clockwise direction. Not because they're down, but it's negative because they rotated in a clockwise direction. Now, this torque over here, I might be smarter to do this formula, because this formula gives distance and force and angle, and that's what we have. We have distance. The perpendicular distance, we'd have to kind of draw the line of action and then figure out what that is. So we'd have to do a little geometry to get perpendicular distance. And so I'm going to avoid that by using this formula. Okay, so this is the R, which is the 9 meters. I'm kind of out of room, so I'll put it down here. 9 meters is the distance. Now, the amount of force is what they call T, the tension, and then sine of the angle between them. And so there's the R, and there's the T, and there's the angle between them, 40 degrees. And it would be a plus. You might have to come back to the picture and look, but something pulling this way, if you put your pen right there, tends to rotate the bridge. So in other words, the cable is how you draw it up, right? You rotate the bridge, the drawbridge, in a counterclockwise direction. And so that's a positive. All right, so maybe taking a couple of steps here. 1.5 times 2,500 times 9.8. And so this would be a negative 36,750 Newton meters. So again, negative because the weight of the bridge is making it go clockwise. The weight of the car is also making it go clockwise, so negative, and it'd be 4.5 meters times 900 times 9.8. And that's actually more torque, 39,690 Newton meters. And I'll say it again, though, even though the car weighs less, it's further out, giving it slightly more torque. All right, then the plus torque, and I'll just go 9 times the sine of 40 degrees. Looks like that's about a 5.79. So 5.79 times tension. Okay, so these two negatives I'll put together, and I'll just do some copy and paste. So there's the first one, enter, and add it to the second one, enter, enter. So there they are together, and on the right-hand side they'd be negative. So if I move it over to the left, it's now a positive, okay? That's how I have it in my calculator. And then if I divide that by this 5.7850, that number there, I will get 13,213 newtons for the tension. Okay, so there's the answer to my question. What is the tension? Now, B is also not quite so easy. In fact, maybe it's even harder. I don't know. But now that we've got A, it makes it a little easier. It says, find then the direction of the magnitude of the force exerted by the hinge. Now, remember, I did torque purposely to get rid of this force. And so that was a perfect recipe if you don't know it and you don't want to find it. But if you want to find it, you want it part of your equation. So let me move away from condition number 2 and move to condition number 1. And I'll break those into its two pieces. I'll do the sum of the forces in the x direction, and that has to be 0. So coming over here and looking at the x direction, and maybe starting with the force from the hinge and just going through left to right, but I would have what I might call the force in the x direction at the hinge. Okay, Then I'll add it to the weight in the x direction. Well, that's nothing. Weight's all down, all y direction. The weight of the car. Well, again, that's all down, no x direction. Okay. Now this does have an x direction. If we know that tension, we can get the adjacent to the 40 degrees, and notice that it's negative, right? This tension is to the left and up, so the x component is negative. So I'm going to put a negative, and I will put the force, 13,213, and multiply it by cosine of 40 degrees. And then grabbing my calculator, I can take the answer that's already there and multiply it by cosine of 40 degrees. And so we're looking at about 10,000, and I'll just go 100 newtons. So there's the x direction. Okay. So now if I do the y direction, some of the forces in the y direction, and again, just going left to right, I'll start here. So this would be the force in the y direction. I have the weight of the bridge itself, so that is 2,500 times 9.8. The weight of the car, and so these are the two forces that have only y. I need it here, but I didn't have them up here in the x. And then I do have a plus. The tension is lifting up a little bit. It would be the sine of 40 degrees. So it would be the 13,213 times the sine of 40 degrees. And so now if I put these into my calculator, minus 2,500 times 9.8, good. Subtract 900 times 9.8, good, plus 13,213, oops, 213, times sine of 40 degrees. And so all of this is a negative 24,000 and something. I move it to the other side, it's now positive. So it's a positive 24,000, and I'll just call it 800 newtons. Nice. All right. Now that I've got the component of the force at the hinge, I can actually get its magnitude by taking the x component and squaring it, the y component and squaring it, and taking its square root. So there's the Pythagorean theorem. So 10,100 squared and 24,800 squared enters, and then taking the square roots, looks like the total force is 26,000, and again, if I go with three significant figures, I better call it 800 newtons. And that's a box. Then if you go direction, and it looks like in the diagram they gave me this theta, so why don't I stick to that? Because tangent theta would be then the y component over the x component. So that's the 24,800 over the 10,100. And now I can get the direction by taking the arc tangent of 24,800 over the 10,100. And so 67.8 degrees. Good. And there's our big pieces and a tough problem. Hopefully that helped.